So homework 2 is returned. Some solutions are posted for that. There's some students, a lot of students did quite well, 18, 19, 20s, with very little off. And then another group of students who did not have some of the computing part done, or not answer some questions for one reason or another, or answer about a different question, like, didn't quite see which numbers were lined up and things like that. What I would like to do, so I think that's important, is being comfortable with material, learning the material. So when it's a question like that, of that concept, that when it goes forward, that things work out well on exams, right? So here's, this is yours probably. This is yours, probably yours,
Yeah,
right?
I'm sorry.
That's all right, so I'll get that recorded. And a handout, yeah.
Thank you.
Yeah.
Thanks.
Yeah. So for homework 2, right, so what you can do for homework 2, right, is you can rewrite the questions that were missed. And submit by Wednesday. It's a break on Friday, and so we won't be here. And then doing it over the weekend, there's going to be another homework that's due at some point next week, probably next Friday, kind of continue with material. But you can rewrite those questions and get back at least half of the points. Right, so if somebody got 12 points because they didn't do part of the computing, or just kind of didn't quite see the focus of how to answer something, and you do that, you can get at least half of that back and at least move up to 16. So that will bring the scores back up mostly into the A-B ranges. Even if somebody got 19 and wants to rewrite that portion of it, they can do that too to get that back. It's open to everybody. And so instead of having quite such a big split, partly because of the computing, right, not getting some of that done, or not describing the graphs, or not including the graphs, and the grader, I think, was accurate. She didn't take off for every little difference. So if somebody reported the minimum and the maximum but didn't calculate the range, she indicated that but didn't take off points for it. And I think that's an appropriate kind of calibration, right? To let you know that you can take the difference to do the range, but it wasn't kind of nitpicking, taking off points every single place that possibly could have had points on, right? But if you rewrite the questions and submit them by next Wednesday, I'll take a look at those. You'll submit the original paper along with what you've rewritten. Now, in rewriting, you can look at the solutions, or they're posted and open, right? But again, the main point is to be comfortable with answering the questions, understanding the material. You can ask about homework 2 in office hours next week as well, right? And so, hopefully that makes things, you feel comfortable about the material, but also, does kind of an appropriate thing in terms of the grades going forward, right? So if you do this rewrite and do well on the rest of them, the homework grades would still be a good part of your grades, right? Okay? Any questions about that? So for homework 3, right? The question. Right? I brought my book for my other class, but not this one. I can tell you about one problem that a number of people were asking about, 2 in particular.
Yeah.
Right? There was a problem with there were 2 women, right, and one man, and a question about Alzheimer's disease. Right? And so there was a question like, what's the probability that only one has Alzheimer's of these 3 individuals? Or let's call the 3 people, persons, M1, M, and then there's the first woman and a second woman. And so if it's only one, you could have one of them having Alzheimer's, but the other 2 don't. Right? So you can have, man has Alzheimer's, the two women don't, right, little lines over top, or that they don't have it. Right? Or you could have the man not have it, and the first woman has it, and the second woman doesn't. That'd be another way of having one of the three. Or these people don't have it, and the third woman does. Right? Those are the three ways you can get that. Right? So if these individuals are independent of one another, unrelated, right, the probability of one of these sequences, by independence, you can do the probability that the man has it times 1 minus the probability the woman has it, times 1 minus the probability. You can multiply these probabilities together. This multiplication is possible because these people are independent of one another. The probability this unrelated woman or man has it doesn't affect the others. So the chance that you don't have it is just going to be 1 minus the probability you do. Right? So this will be the probability that the man has it times 1 minus the probability the first woman has it times 1 minus the probability the second woman has it. And those probabilities, right, are the things that come from the table, where they describe the different chances. And so if you calculate these three, right, and add them together, that's going to be the probability that only one of them, exactly one of them, has Alzheimer's. So one of the questions was, what's the chance that a woman has Alzheimer's, and there's only one out of the three? Well, only one, and a woman having it, right, is really fulfilled by just these two. So you can add these two probabilities and divide it by this other one, and that gives the probability that, given that one person has it, what's the probability that a woman has Alzheimer's, given that one person does have Alzheimer's? With conditional probability, you can write it as these two things happen together. So a woman has Alzheimer's, and abbreviate, and one person has it. Well, and then over the probability that one person has it does have Alzheimer's. Well, this is a little redundant, right? So if there's a woman has it, and it's one person, it either has to be the man not having it, woman one has it, or woman two has it. Right? One of these two things qualifies as at the top, whereas all three qualify as the denominator. Right? If you calculate those and divide it by that, you get that answer. That was one question I got asked a few times. But I don't remember exactly what the other variations of that was. The other question that was big was about the preterm birth, gestational age of birth, and low birth weight. And so that was a little bit more information, kind of interesting, right? Because it divides up, kind of might be a realistic question you might want to know, right? So in this one, we did some trees that went, with two categories, in the two different categories. This tree had a bunch of them. One was 37 weeks, one was 36 weeks, one was like 34 to 35, if I'm remembering correctly. And then there was a couple others. I don't remember the lowest one, if there was another range in here. And then there's some probability for were there 5 groups in all? Yeah, and these things added up to 1. Okay. And then there's a certain chance of low birth weight. Less than 2,500 grams, low birth weight, or normal birth range. You can really just concentrate on just the chance of a low birth weight, because all the questions are about that. And I think for even the term births, there was like a 0.029 probability of having a low birth weight among babies born at term. There was a fairly high probability of ones born early, right? Was that 70% or something like that? Or was it more? Right. It's quite high. So is low birth weight and gestational age at birth independent of one another? The quick answer is no. The probabilities are changing, right? Depending on where you are, which category you're in terms of gestational age category in this here, the chances of low birth weight are changing a lot. They're not independent. So one was to calculate just the probability of a low birth weight. How can you go about that?
Would you take the probability of having like the gestation period times the probability of the low birth rate and that amount?
Yeah, so if you take P1 are in this category and 70% have this, so you take this times this, plus P2 times this one. This was also pretty high. I don't remember the exact numbers. Times that, P3 times this one, P4 times this probability, P5 times that, and add them up. And so that's the low birth weight percentages weighted by what percent are in the population. There was a big percentage that were down here, down low. And I think the answer comes out to be about 0.07% overall, right? Maybe with another decimal or two, right? If you follow it all through. But it's a weighted average of all those conditional probabilities. So that's kind of a generalization of just like a 2 by 2. It's just like a 5 by 2 thing. I'm going to ask, what's the chance, so a baby is born with low birth weight. What's the chance that it had a certain gestational age? Right, so that's Bayes' theorem, that's reversing the probabilities. Right? So the probability, say, age, 34 to 35 weeks. It's not exactly what it asks in the question, but given low birth weight, the way we did these type of problems, you can do age 34 to 35 and low birth weight. And the thing that goes on the denominator is that first thing you calculated, the chance of low birth weight. But this one, of these things together, right, you're told age 34 to 35, and then you're told the risk, probability, in that age group, that gestational age period. You can multiply those two things together down one of those tracks. Over that number, there was about 0.07 and get a chance, it's low birth weight. What do you think is going to happen to these different age categories if you get an early birth, preterm birth? Is the probability going to go up or go down if you know that this baby is low birth weight?
Go up.
Probably go up, right? Low birth weight was a lot more common in early babies born prematurely, right? And so, on the other hand, term babies, 37 weeks or more, low birth weight is fairly uncommon. Right? Not totally uncommon, 3% or so. So it is low birth weight. It's not as likely to be term birth. Those were a couple. Right? Any other questions that you want to ask about that? Yes?
The ones about like the PB plus and PB, I don't know how to do that.
Okay, yeah. So the we didn't talk exactly about PB plus in PB. We talked about sensitivity. The good question, good chance to talk about this. And that sometimes you report among those that are truly positive, they have the disease or the condition that you have, or the kind of gold standard test says they have whatever you're concerned with. Right? You can ask, do they test positive? Does this new test or this cheaper test or whatever, this indication say they're negative or positive? Right? Specificity is a similar thing, but on the negative side. Of those that are true negative, right, and do not have disease or the official status, what's the chance the test you're running is negative for them? Right? But sometimes you want to reverse this. Right? Given that somebody tests positive, what's the chance they really have the disease status? So predictive value positive is the probability that somebody is truly positive and has the disease, given that they've tested positive. And predictive value negative is kind of the same thing for the negative. So predictive value negative is probability of true negative given that you're tested negative. And you get to answer this based on a two-way test. There was kind of two ways of doing this. One was an automatic. I think the automatic was on this axis, on this side, right? And there's two cutoff values. And so one was test positive and one was test negative. Sometimes I wrote positive, negative, but I think I say that as they're setting it up, less than 10 or not, one's defined as testing positive. This one is another test, but it's a manual one where maybe there's a little more intervention and people are looking at it, maybe it takes a little bit more. And this is called, you can call this the true negative, true positive. Say these counts are A, B, C, and D. Well, this is about kind of figuring out which row and column goes in the denominator. So if you truly have the disease, right, the ones that truly have the disease, well, if this is up here as a true disease one, this is positive, then B plus D has the true disease. Right? Some of these people test positive and some test negative. So this is, you're reporting D divided by D plus D. In the specificity, though, true negative, no disease, if it's this column, right, the denominator is A plus C. And if this is negative, then there's an A there, whatever that count is, it's a fraction. And this test doesn't give you really high values. These percentages are not working out to be 0.99 or anything like that. There's some that are kind of small. The other way it could be reported is this other thing, a predicted value positive. What's going to be the denominator in that calculator? Yeah. Yeah. Testing positive, right? C plus D. And what's the numerator? Testing positive. Among those that test positive, right? Yeah, so D again is this numbers that are positive, right? So D is in the numerator both places, but the denominator is a little bit different depending on whether you're conditioning on you're in this row or you're in this column. What's the denominator of predicted value negative?
A plus B.
Yep. A plus B. And the negative again is this A one over there. So you calculate that, right? You get that fraction. So those are I think that's mostly what people students asked about, right? What you all asked about during office hours or email. Any other? So, given this, right, why don't you take some time to finish this one up? We are going into a break. It would be easy to extend it until Friday if we didn't have a break. So, and there's a rewrite for this other one, right? So it's okay with me if you hand this in on Monday, right? Because again, I'd rather have you feel comfortable about it, learn it, right? Get the answers, be able to incorporate this information, and Monday it is over the 4-day break, but hopefully you've done most of it. So one way or the other, work out that you can get that part done. If it comes in on Monday, we can get it graded and back to you, before the next one comes in, and I can address the regrading of the two. Right? So let's make homework 3 now due on Monday. If you finished it and want to handle it now, and there's a few here, that's great. If you want to take yours back and recheck anything, that's fine. But any other questions? But as going forward, we can certainly, in class, do more problems like the homework and try to have a problem day to talk about things before do. I think that's a good idea. I mean, so these are getting good questions, relevant questions to things, figuring out details, and it helps me a little more complete, so we can keep doing it like that. So. All right. So let's do that. The homework 2 rewrite part, I said we should do Wednesday. We'll keep it like that. Right. Because you might need to use the computer to do a little bit more of that, to go back and finish that one up. So, okay. So what we're going to do today is introduce this concept of random variables. We talked about probability of different things, but now we link the probabilities to numerical outcomes. And the handout is a good place to start. Does anybody need a copy of the handout? I think Right. So we're going to have some random phenomenon. It's going to have different outcomes. And now we're going to tie that to numerical outcomes, right? And so we're going to record numbers, 1, 2, 3, 4, 5, 6, or the count of number of children at a household, the count of the number of times that something happens. It could be any number of things. If you're working in CERN, in their subatomic accelerators, you could be counting the number of particles that spin off in there, and your counts might be in thousands. Right? If you're working in astronomy, you might count the number of types of planets and stars you see in a certain thing, but it's going to be counting things. Right? You can count the number of individuals with certain characteristics, and so on. Generally with random variables, we refer to them as capital letters toward the end of the alphabet. That's the convention. We'll have notation like that, X, Y, Z, W, V, but I usually would write out the word, what does it mean, this random variable, what is it actually measuring for you, what's it recording. Maybe choose a letter, if that's corresponding to that phenomenon, but X is kind of a default. There's X is which is the random variable, which means that we're going to measure something random. Right? And then there's the little values that are associated with that. Right? So we try to distinguish those. Probability distribution for a random variable gives a list of all the values you can have, along with the probabilities of each one. Right? So you're rolling a 6-sided die, the probabilities of the 1, 2, 3, 4, 5, 6, or you're randomly picking people and recording the number of televisions they have at home, and you're recording 0, 1, 2, 3, and so on, and the probabilities associated with that. Right? And so as we get probabilities, there's a number of ways you can tell people the probabilities, you can show them a graph of probabilities, you can show them numbers, and for a few of the random variables we'll do, eventually we'll show a formula, where you don't list them all out, but you have a formula that works in a number of situations. It might depend on parameters like a proportion or a mean or something, but it's going to translate into these probabilities and different outcomes. And so let's do a couple little examples. Right? So imagine you're drilling for oil someplace, and there's a probability 0.1, 10%, that when you drill you make $1,000. And the scale of this is a little artificial. So oil drilling, maybe it's more like $10 million is what you would make. But let's say it's $1,000 just to have some positive value. But with probability 0.9, you lose 100. You put in the investment to build everything, but it doesn't work out. So how much do you expect to make on average? Well, there's $1,000 that you can make with 10%, which is 100. There's a 90% chance you will lose your money, so that becomes 0.9. Right? And so you expect on average to make about $10 every time you do this. Now, every time you go out and dig one of these wells, you either hit it big and make 1,000, or you lose your investment and lose 100. But kind of in the long run, now if you do this a bunch of times, you will sometimes make 1,000, sometimes lose 100, negative 100. 90% of the time it's going to be on the negative 100 and 10% on that. And so in the long run, you come pretty close to about $10 per time on average. Right? You can imagine another scenario, right? Maybe we'll put this other scenario on the handout. So in the first oil scenario, there's $1,000 as a value. It happened with 0.1, negative 100 as a value with 0.9. The expected value of a random variable is calculated by taking the sum of the values we can have times their probabilities. And a weighted average of the values by their probabilities. And so in this case, and sometimes that's expressed as an expectation. Sometimes the book will use the Greek letter mu, kind of the theoretical average of this random variable. So in this case, it was the expected value or average was 1,000 times the probability. And then the negative 100 times 0.9. So 100 minus 90 was about $10 on average. Now you can imagine a difference. The second oil scenario that's described on there is a different company, it's a different technology, different area of the world. Things are just different. The probability distribution is just different. It's not the same returns. Imagine it's $1,000 with only 5%, but you get $100 benefit with about 15%, and you lose your 100 where there's nothing there at all about 80% of the time. So this one has 3 values, and so 3 probabilities. How does this one work out? Is this as lucrative as the other one? What's the expected value in this case?
Negative 15.
Negative 15. Is that on the page of the handout?
Yeah.
Yeah, so that's on there. So how do we get that one? Right, so following along, right, taking the values times their probabilities. Right, 1,000 times the 0.05 plus 100 times the 0.15 plus the negative 100 times 0.8. So now you end up with this 50 plus this is 15, and this one is minus 80, so you end up with negative 15. So every time you do it, you're going to get 1,000 or 100 or negative 100. Those are the only 3 values you can ever possibly really see. But kind of the theoretical average, the long run, if you do this a bunch of different times, a bunch of different wells, you'd be losing about $15 on average. It would be unfortunate if you got your first 2 out of 1,000, you think you're in a really good spot and keep going, right? Because in the long run, it's going to drag you down and you're not going to get it. So, anyway. So that's some of the essential idea. Right? There's values and probabilities, and we can look at means. We also look at variances. Here's a second example. Imagine you're randomly picking people who are driving along, right? Cars going by, right? And you're counting the number of windows they have up. Maybe this is a bigger part of a study about energy efficiency, how much people drive, what do they do in their car, how much time do they spend in their car, and you're doing how do they use the air conditioning, right? Things like that. And so, but one question ends up how do you drive with the windows open or closed, and they count the number of windows that you typically have. Right? So that's the thing you're counting. And a car has 4 windows, most cars, right? Many cars. 0, 1, 2, 3, 4 are the different values, how many windows are open. Imagine that in the summertime, this is the distribution that's out there. 40% of the time people have 0, 20% for 1, 10% for 2, so on. But in wintertime, this is the distribution. People have more windows closed, maybe it's colder, so they have their heat on or something. But every once in a while they have open, maybe they're fogging over and need to let some moisture out or something, whatever. How do these 2 probability distributions compare? Yeah.
More people are likely to have the windows shut in the winter.
Shut in the winter, yeah. More is at 0 here, that's all 4 shut. Yep. All right. Anything else? So these type of things of describing, like with describing data, you can pick up on any number of characteristics that might be different. Yeah.
It's more common in summer to have all 4 than like just 3. which is
Yeah,
common.
yeah. So summer 3 and 4 were bigger than they were down here. Right? Which one do you think is going to have the higher average? One thing you can do is, if you can put these things into a graph, here's a little graph that I made with a ruler and straight edge, right? Here's the winter time on top, 55% here and 20%. I think on my piece of paper, this is about 5.5 inches. And so, actually make it try to look proportional. And this is the summertime. So this would, illustrate the distribution that you would likely see. Right? So you can either give me the table with numbers, or you can give me this figure, and I get an idea of the values. So which one do you think is going to have the higher number on average? Yeah.
Well, I think that's kind of difficult because it's like they're both kind of similar. Because if you took off the high and the low numbers, they're pretty much the same. Like, there's not that much difference in either of the numbers.
Yeah, so they have the same range. They both, 0 through 4 are the 5 possible values you're going to see. Right? And it's kind of similar in the middle, 20%, 20%, 10%, 10%, right? But in summertime, a little more chance on the high numbers. Right? You're going to get 4 and 3 more often. Down in the winter, you're going to get 0 and 1. Right? So that's going to mean that the average is going to be higher in the summertime. Right? So if we do that one. So we do our window example, and we look at summertime. The average number of windows, or the expected value, let's call it summer. S is the number of windows in summer. There's this one. 0 times 0.4, 1 times its value 0.2, 2 times 0.1, 3 times 0.1, and 4 times 0.2. So you're adding together 0 plus 0.2 plus 0.2, 3, 8, and that is their 1.5. The units on this are really windows. That's what we're counting. Right? Sometimes you might not think of these counts as having units, but it's counting something. It's counting windows in this case. You do the same thing for winter. Right, the average in winter is going to be calculated the same way, but now the probabilities are different. And if you put the numbers in, it comes out to 0. Where is it? 85. There's more probability stuck at 0. There's less up here in those multiplications, so it ends up being a little bit smaller. Right? On these graphs, the averages actually end up falling at things that if these were weights on a balance beam would be kind of a fulcrum, a balancing place, kind of equal weight on either side. This one has to be pretty far back because there's so much here, whereas this one has to be more out to balance. In any case, but kind of where you see kind of a high, you need to balance. Where the mean really ends up being the expected value for car windows on this page, 1.5 and 0.85. Again, right? But any questions about it? So that gives us something that we get the values. We could talk about the probability you're less than 2 or bigger than 2. You can do a lot of descriptions of the probabilities for those. And you can do the mean. There's also a standard deviation. Deviation is a random variable. Right. So it measures spread and the values we would see if we did this experiment over and over again. So we had a bunch of cars and took their values. Maybe one time you'll get a 0, and then you'll get a 4, and a 1, and a 2, and some more zeros, a 1, and maybe a 3 eventually, and so on. Right? Those values you could see if you did the experiment over and over again. Essentially measure the random variable, record it several times. Those have a spread, right? A standard deviation. And so we can calculate what's the theoretical standard deviation you would have in a very large collection of measurements. Right? So this formula is a little bit more involved. The variance of a random variable, a discrete random variable that has counts or integers. We're going to take a sum over all the values that we can have. We're going to take the value minus the mean squared, and then we're going to multiply it by the probability that we have that value. So this whole thing is inside the summation. So take each value minus its mean squared and multiply by the probability. So there's a few steps. We'll illustrate it. An alternative way of doing this that the book presents is an equivalent computation. If you just take the x's, the values themselves and square them times their probability. That's just like an average on the x squared scale. And then outside of that, subtract the mean squared. So first you do all of this. Sometimes this is easier to do, particularly with values like 0, 1, 2. I can square those easily. Right? I can't take 0 minus 0.85 and square it so easily, or 3 minus 0.85 and square it so easily. So anyway, either one of these things work, and then standard deviation of x of our random variable is the square root of the variance. And that's how we calculate a variance for one of these random variables. So let's look at the car example. Right? Or not yet, so what are the car examples? So we had values 0, 1, 2, 3, and 4. And let's do it in summertime. In summertime, the average is 1.5. And using or get comfortable with a few of the symbols will help read some of the book and some of the things that are in there. A lot of what we'll do in communication of this in terms of homework or exams is you can write a lot of things in words. So the probabilities of these different ones were 0.4, 0.2. Just draw some lines to keep things straight. 0.1, 0.1, and 0.2. 4, 2, 2. So 6, that adds up to 1. It's always good to check that. Now this is x. Right? So the one version of it took x squared. So we take x squared, we're going to get 0, 1, 4, 9, and 16. And we're going to take each of these squared values times the probability. So you multiply those, you get 0, 0.2, 0.4, 0.9. And this one gives you 4 squared is that 3.2. We're going to add those things up. 6, 15, 17. So 4.7. Is that right? 3.2. Yeah. So the sum of x squared times the probability is this 4.7, and the variance is that number minus 1.5 squared, 4.7 minus 2.25, which is 2.45 is the variance. So the standard deviation of x, square root of that, 1.57. And that's back on the 1.57. That's back on the scale of windows for this example. That kind of goes into the mechanics of that calculation. Any questions about? Yeah.
Just what exactly is like the P of uppercase X? So
This
it's
is
just
probabilities?
Probability of
That the-
value equaling.
Probability that the random variable takes on that value.
Oh, okay.
So the probability, and it's here, these are the values x like 0, 1, 2, 3, 4. And these are the probabilities that it's 0, 1, 2, 3, or 4. Come back. In the wintertime, do you think the variability would be more or less? Maybe we'll go back to the picture. Where's the picture? Oh, it's on the left. That's, here's this picture. Summertime's in the bottom, wintertime's in the top. So the standard deviation, the variance, they measure spread. How spread out are these 0, 1, 2, 3, 4 values that you're going to get? They both have this, same range. 0 to 4 is the minimum maximum. Which one's more concentrated? Which one's more spread out?
Winter's more concentrated than the summer. Summer's more spread out.
So winter's more concentrated, right? You're going to get mostly 0s and 1s. A few, then a little bit more extreme, right? That's going to be more skewed, that's true. But most of the values are a little more concentrated. Whereas here, well, you're going to get some 0, 1s, some 3, 4s. It's going to move, random sampling. You're going to get more and more spread. So the summertime's more variable, and its standard deviation is going to be bigger. Calculate it. That was standard deviation is this. So in summer, the standard deviation was 1.57, 1.7, and then in the winter time it's less. The standard deviation a little bit less, 1.39. Not a lot less, but still less because it's winter is going to be piling up on the 0 ones and not as bouncing around quite as much. So that's a lot of the essential ideas of this. But a number of these other random variables. So if you had, so for example, you had 10 deer ticks, and 3% of the population is infected with Lyme disease. And we're going to take 10 and sample them and find out, from this sample of 10, what rates of infection you have. So X is going to be our variable, the number of deer ticks in our sample with Lyme disease. What values are we talking about? What do we have for values? We'd have 0. You'd have 1, 2, 3, 4, or all 10. Right. So our values we could see from a sample of 10 would be 0 through that. Yes?
How could it be 0 through 10 if there's only 3% of the population affected?
So 3% of the population is affected. We're not sampling with replacement in any way. So imagine this is a huge population.
Okay.
Right? There's thousands and thousands of ticks.
Oh,
We pick 10. Yeah.
Okay.
And the general rate is 3%. Well, we'll figure out to, with independent events, you can actually, and with stuff that we'll do when we come back to, binomial, you can figure the probabilities of these different things. Well, 97% are not infected, and there's 10 that are not infected. So 97% times 97% and so on. So 10 is the probability that none are infected. And with some rounding, this comes out to be about 74%. So in about 74% of the samples of 10 ticks, we wouldn't find any if there's only a 3% rate. The probability that we get 1 tick out of 10, but there's 9 that don't have it, and there's 1 that does, we multiply those probabilities. But there's actually 10 ways we can pick one of those ticks, so there's actually a 10 multiplier on there. And the rationale for that is that calculation is a slight extension of things that we've done. We'll redo that, so you don't necessarily, I'm not really explaining fully or at length about what that is about, but that comes out to be 0.23. The chance for 2 ticks ends up being, if you calculate that, about 0.03. And all these other outcomes are about, they're not exactly 0.0, they're tiny, right? But they're basically like, they're 0% chance to 2 decimals. It might be 0.0001 or something like that. Yeah.
Is that a 10 in front of the,
10, yes, it's the number 10.
and that's there?
So this is the formula that actually would calculate that probability, right? So if you have 1 tick that's infected out of 10, right? You could be the first or the second or the third and so on. So this probability occurs with 10 different things. We had something kind of similar to that, earlier today. Right? If you think about, there's 3 people, and 1 of them has Alzheimer's. Right? We looked at the probability that the man had it, but not the 2 women, or the woman and not the 2 others, or the second woman and not the 2 others, and added those together. Right? There's 3 things we added together. The probabilities changed each time because the men and women had different rates. So in this case, the rates don't change. but if there's 10 ticks, we gotta pick one, so there's 10 choices there, so it's kind of analogous. So anyway, that would be the probability distribution for the number of deer ticks. And on the other hand, you had some area with a 6% infection. Then things would change.
Professor Larson,
Yeah.
can you just explain where those numbers came from again?
So, yeah, so we will, this is, right, so if we had 10, 10 of these ticks, right? And we're gonna count the number with Lyme disease. So we could get a sample with none, so 0, or we could get 1 of the 10, or 2 of the 10, or 3 of the 10. Right? So we get different values we could have. Values we could possibly have were 0, 1, 2, 3, etc., up to 10. Right? And to give a probability distribution like we're doing today, we want to give the probabilities. And this is one case where we would use some of the rules that we've done to calculate probabilities. And so this is kind of probability of no ticks with the disease, and probability of 0. Right? The probability that they're all negative for the disease. And if 3% have the disease, then 97% of the population doesn't. And so that's the probability that a tick is positive for it. Randomly selected tick. So 1 minus that is 0.97 is the probability that they're negative. So that's for just 1 tick. If we're testing 10 and they're independent of one another, they're not in just one nest, but somehow they're independent of whether they have the disease. The chance to get 10 is going to be 97% for the first one, 97% for the second, 97% for the third, and so on. All right, so this is the probability that the first is negative, this is the probability the second is negative, etc. And the probability that then the last one, the 10th one, is negative. And so the first one is the point, it's 0.97, 97%.
Is that just because you did 0.97 to the 10th?
Yeah.
But I don't know where those other numbers, like.
Some of the other ones came from.
Yeah.
So the kind of calculations, how we got to those, we'll explain more about that.
Okay.
Right. Yeah, this is an example, actually, of a binomial random variable. And we will do it in detail. We'll do it in detail next week. So I kind of jumped ahead with an example. Kind of the deer tick testing, could be, interesting as something that they really are testing ticks to find out what are infected across things. But the formula is to come up with these probabilities. We'll explain more. We'll go step by step and do it.
So does that 0.74 mean that it's a 74% chance that none of them have Lyme disease?
Yes.
Okay.
Of these 10 ticks, the chance that you get none with the Lyme disease turns out to be about 74%. About 23% of the time, you would get 1 of the 10 having Lyme disease. So yeah, you get a positive result about 23% of the time. If there's only 3%, and these are really a random sample, 2 is pretty rare, and getting any more has tiny, tiny probabilities that you would, the chance that you get 10 ticks altogether that have it, if it's really independent, is pretty minuscule. So we will do this in more detail, but for now you can maybe think about this as another probability distribution that has tiny, tiny little probabilities after that, but different. So sometimes our discrete ones will come from a process like this, which is a certain number of samples, a certain number of discrete issues, a certain number of organisms, a certain number of people, and do a test or evaluate them and say, how many out of this group have a condition or infection or whatever we're looking for. So, yep, we're connecting the probabilities to numerical things that we're going to do. We can look at the probability distributions, describe them, calculate averages and standard deviations. And as we go forward, we'll get more formulas like the binomial one for special cases. So we'll do a couple of those, kind of illustrate what's going on. Not a lot, but it's all right. Oh, I did. Okay. Okay.
You get the.
So you didn't get a grade. Let me double check.
Okay. If not, I can. Here, you can copy it.
Thank you. Yes, hi. Yeah, so you guys, everything is taking you away. Yeah, so
You guys stay on campus, you mentioned?
Yeah, I'm going home.
yeah, so if you do that one,
Yeah, no,
She lives near you last night.
why don't you do that?
Yeah, I know, I guess
Draw that
Oregon was
on
good.
track.
I used to go to school there. You know,
You
Oregon.
went to Oregon?
Yeah, yeah.
Kids like go there?
Where?
Words.
What school? UVO.
Doing the
No, I went to University of Portland. It's like a small school. Yeah, but there's like hella kids from California. It was insane.
Yeah.
Like, literally, everyone from California moves up to
That's the
Portland.
go-to. Yeah.
Yeah, I feel like it was mostly Bay Area kids though.
Is what?
Bay Area?
Yeah.
Yeah.
Did you like it?
No, I love living in Oregon and stuff, but I just didn't like my school. So
You what?
I just didn't like my school. So
Oh,
I was like, and then I was like getting homesick, so I was like, alright.
Yeah.
But yeah, how do you like the 6-hour flights and the jet lag?
Oh, I hate it.
No, it's so
It's
bad.
terrible.
And you have like the worst end of it. I feel like I liked it because like when I was just like going there, I would like wake up 3 hours earlier. So I'd like my 8 a.m.s were so nice. I was like, oh, it feels like freaking 11 a.m. Like I'm cooking. And then I'd come here and I'd just like sleep all day and I'd be like, whatever. But I'm like, if I had to come here and take classes,
Yeah.
like that would be so brutal. Do you have to stay for?
Thank you.
Weekend?
I got military training in Rutland, so technically, yeah.
Yeah.
Too, right? And lacrosse.
Yeah, you're busy. All right, well, have a good weekend.
You too.
And you too.
Thank you, and you too. Have a good one.
Yeah. Yeah. Thank you very much.
Short military training down in Rutland.
Yep, yep.
So, good luck.
Thank you very much. Appreciate it. You have a good break.
You too. Come on in. I'm just saving a file, and I'll be there.